Big Bang is one of the most well-known and most misunderstood of all modern science theories. Indeed, when I talk to people or read viewers' questions, it's very clear that confusion abounds. Since confusion impedes progress, we need to clear up that confusion to make further progress. That sounds like an excellent topic for this week's episode of Subatomic Stories. The Big Bang is the current scientific understanding of the origins of the cosmos. The visible universe, which is as far as we can currently see, was once much smaller and hotter. About 14 billion years ago, something happened, we still don't know what in detail, and the universe began expanding rapidly. We know all of this to be true for several reasons. First, we see the expansion of the universe because distant galaxies are moving away from us and more distant galaxies are moving away faster. Second, we can look at the hydrogen and helium in the universe, and that ratio is exactly what the Big Bang predicts. And third, we see the remnants of the primordial fireball in a bath of radio waves hitting the Earth called the cosmic microwave background, or CMB. I don't want to talk about any of that. Defending those statements is the subject of another video. In this video, I want to talk about the ways in which many people misunderstand the theory of the Big Bang. And, in the interest of full disclosure, I had many of these same misconceptions when I was young. So the first misconception is the hardest to get your head around. Most people think of the Big Bang as like a firecracker or a grenade that went off. They think of empty space without any matter in it, and with all of the matter and energy of the universe concentrated down into a single point. Then the universe exploded and spread matter and energy through space. That didn't happen. A spin-off of that idea is that there is an edge of the universe. In this misconception, if you look far enough away, there's a spot in the universe where there's nothing, simply because the shockwave of the Big Bang hasn't got there yet. That isn't true either. Another common incorrect idea is that the Earth is at the center of the universe. This thought arises because no matter what direction we look in space, we see objects moving away from us. That could mean that the Earth is at the center of the universe, but the universe is huge, and that's just incredibly unlikely that we happen to be at the center of it. There has to be another explanation. By the way, these are all kind of sensible ideas, especially given some of the animations you see on the internet. All of them look very much like the Big Bang was some sort of familiar explosion. I've even used such videos, mostly because they're visually interesting, but they're very misleading. So let's start with what we know. We certainly are at the center of the visible universe. That's not so surprising. The universe is big, at least 500 times wider, and with a volume 125 million times bigger than we can see, maybe even bigger, and we're sitting in it in some random place. There's a sphere surrounding our location that marks the farthest distance we can see. That's the visible universe, but it's not the entire universe, not by a long shot. For the purposes of discussion, we can assume that the universe is infinite in size. If it's not, that doesn't affect what I'm talking about here. All that matters is that the size of the entire universe is much larger than the size of the visible universe. Okay, so to get a better idea of what the Big Bang really was all about, let's start with this picture here. The grid is a two-dimensional representation of the universe. The dark circle represents a sphere centered on the Earth. This is the visible universe from our vantage point. The grayed out bit are sections of the universe so far away that light hasn't had time to get here yet. You'll notice that the universe in the grid is much bigger than the visible universe. Okay, so let's see what happens if time progresses in the way we experience it. The visible universe, indeed the entire universe, expands. We can see that because both the circle expands, as does the grid. That's what's going on today. Now let's reverse time and see what happens. As we go back in time, the visible universe gets smaller and the size of the grid gets smaller too. This represents a time when the visible universe was half as far across as it is today. Let's run the clock back farther. When the universe was smaller, it was hotter. This graphic represents that by turning the color orange, then yellow, then finally white. You'll notice that the grid in the visible universe is getting smaller. If we run the time all the way back to time equals 0, you see that the visible universe is very small. In the simple version of the Big Bang, the size is literally 0, but we know that's not completely accurate. The visible universe was merely super small. But you'll notice that the grid still covers the screen. That's because even though the distances in the universe were closer together back then, it was still infinite in extent. Then the universe began and the expansion started. You see that no place in the universe was special in any way. Space just began to expand, and it continues to expand today. So that's what the Big Bang Theory really says. The universe was smaller, but that just means that the distance between points was smaller. The universe itself could well have been infinite in size, even when it began. Then something triggered the expansion, and we don't know what, and the universe was hot and distances between points grew in size, and the cosmos cooled into the universe we know and love. Now, my example had the universe infinite in size, but what I said is also true of a finite universe that is bigger than the visible universe. If the 2D version of the visible universe were painted on the surface of a globe and the globe shrank, that's basically the same thing I've described. That's a lot to think about, so now I'll give you some time to mull it over. I'll do a follow-on video that talks more about the stages of the universe as the expansion began. But it will be a lot more accurate if you have this mental image in mind for that video. Okay, so let's see what questions you have for me this week. Question time. This week the questions were quirkier than normal, which somehow seems appropriate. Quirks for quarks, so to speak. Ojama Black notes that a nog is smaller than a quark. Hi, Ojama. I'm completely embarrassed that I never thought of that joke, and it's about my favorite TV franchise to boot. I henceforth pledge that if in my career I ever discover and name a particle smaller than a quark, that I shall call it a nog. Thanks for the great idea. David Zaring asks me if the questions posed here provide some insight or direction to investigate. Hi, David. No, not really. The thing is, pushing forward knowledge is hard work. You have to know about all of the data that's gone before, and that takes years to master. It's extremely rare, and I mean extremely, that a casual question points in a direction that is both original and productive. On the other hand, there have been plenty of witty and creative jokes, so there's that. Just Paolo asks about the hot and cold spots in the cosmic microwave background and what that really means. Hi, Paolo. That's a great question that shows you thought about it really quite a bit. So here's the deal. There are a class of objects called black bodies which absorb all energy that hits them. Black bodies heat up and then emit electromagnetic radiation over a range of frequencies, and the range depends on the temperature. For instance, for very hot things, hot enough to glow invisible light, the cooler things glow red, and then as they get hotter, orange, yellow, blue-white, and finally into the ultraviolet. But even though we see a specific color, they emit over an entire spectrum. For instance, this is the distribution of wavelengths emitted by black bodies of different temperatures. Notice how the curves change for different temperatures. Hotter means shorter wavelengths. For the CMB, it's similar, but the CMB is much cooler, so what is emitted is a spectrum of microwaves, which have much longer wavelengths than visible light. So for the CMB, astronomers look at the spectrum at different spots in the sky and figure out what temperature each spectrum corresponds to. For the CMB, the differences in temperature are tiny, meaning that to the eye, the spectra would look the same. But they are slightly different. Good questions. Martin Heermans looks at the fact that the charge of the down quark is exactly 1/3 that of the electron and states that he thinks that it's telling us something important. Hi, Martin. Yeah, me too. I just wish I was smart enough to figure out what it was. I always wanted to shake the hand of the King of Sweden. Tobias Toman basically asks if particles like protons could exist, but with other quarks. Hi, Tobias. They sure can. Protons are particles of a class called baryons, which includes 3 quarks, specifically 2 ups and 1 down. Charm and top quarks have the same charge as up quarks, and strange and bottom quarks have the same charge as down quarks. So, can we make baryons with combinations other than 2 up quarks and 1 down? Well, yeah, we can. There are baryons with 1 up, 1 down, and 1 strange quark called lambdas. Then there's the one with an up, a down, and a bottom called the lambda sub b. In fact, you can take any combination of 3 quarks from the 6 known quarks and make a baryon. For instance, bottom, bottom, bottom is possible. However, there's one thing I haven't mentioned. It takes about 10 to the minus 23 seconds for a baryon to form. The lifetime of top quarks is shorter, about 5 times 10 to the minus 25th seconds. So, top quarks decay before baryons can form. So you can't make baryons with top quarks. Thus, really only the other 5 can be found in baryons. That's a total of 125 different types of baryons, and if you allow for different combinations of spin and motion inside the baryons, there are many more combinations, and many of them have been observed. But none of them have top quarks. It's all very amazing. 5 quasi-stable quarks can explain hundreds of different particles. And finally, Dwight Schrute notes that the video length of 1337 points to some very elite physics. I admit that I had to Google that, but he's absolutely right. Everyone at Fermilab is 1337. And that sounds like a great place to wrap things up. If you enjoyed the video, please like, subscribe, and share. And look forward to upcoming videos because, even at home, 1337 physics is everything.